Okay, so this is going to be lesson 4.1 part 2. I'm assuming that we got about halfway through the lesson in class today. So here's the second part. I'm assuming that you got through this slide, this side. Of course, we looked at the objective, learned about the basics of exponential functions. We learned that the a is the initial amount, the b is the growth factor. So we learned about the parent function, and we looked at a graph here of some of these functions. What I want to do on part 2 is basically show you the horizontal and vertical shifts. And these are just like our square root and our cube root functions. They work very similarly as far as the horizontal shifts. So to graph these functions, we're going to do, you start out by graphing like the parent function. Just start out by graphing that one right there. And then after that, we'll figure out the shift. This of course causes the horizontal shift right there. And this one causes the vertical shift right here. And remember, the only tricky thing about this is that the horizontal shift, you have to set this part equal to 0. And usually you can do that in your head. And then just solve for x. Like x plus 2 is equal to 0. And so x is equal to negative 2. And so that's that just means there's a horizontal shift in this direction, the left, and we're going to go 2 units to the left. And then the vertical shift is pretty easy. It's exactly what's written here. So this one means go up 1 unit. So when you combine the two, you have the shift. You have a shift in the horizontal direction and a shift in the vertical direction. So to do the first part, well, we typically just use some values here, and I'll show you how to do that real quick. Usually what we do is maybe start off with negative 2, negative 1, 0, 1, and 2. These are kind of our default values for the exponential type functions that you'll be dealing with in chapter or section 4.1. And so you just substitute these numbers in. Now, it might be helpful to have a calculator for some of these. You're just going to plug those numbers in for right there. So the function we're looking at here is 2 times 4 to the x. Okay? And so if you put a negative 2 up there, what we'd have, I'll do the work over here. You have 2 times 4 to the negative 2. Well, using your property of exponents, what we do is we move this one down to the denominator. So this becomes 2 over 4 squared. And of course that's equal to 2 over 16, because 4 squared is 16. And then of course this reduces down, this cancels off here and gives you 1/8. Now if you put that in a calculator, 1/8 is equal to 0.125. Now, here's the thing that's a little bit confusing. As we saw in the first couple examples, there's always an asymptote right here, okay, along the x-axis. Okay, so one of the things that was weird to me, whenever I put negative numbers, I sometimes expect a negative answer. And that doesn't happen a lot of times with these exponential functions. You might not get a negative answer. So the way we get a negative answer in some cases is by shifting. So eventually, after we do the parent function, like I said, we will shift 2 units to the left. Well, that's going to move the whole function over to the left, but then this one moves it up 1. In some cases, we'll be moving it down, and then it becomes negative in that sense. Anyhow, I always kind of found it weird when I didn't see too many negative numbers here, and that's not uncommon when you have exponential functions. So just be aware of that. So we just repeat the process. We're going to just plug in these numbers. I'm going to plug in -1 now. So let me just erase this now and let's see what happens. After a while, you'll be able to do a lot of these points in your head and you'll just be able to put them in. But let's just go through it step by step. We have 2 times 4 to the -1. Well, again, the negative exponent, we use the property of exponents that says, oh, well, we can move it down to the denominator. And then that exponent becomes a positive one. So then this becomes 2 over 4. And of course, that's just simply equal to 1/2. And so, for here, we'll put 0.5. Okay, so just keep going through here. Now, the next point would be 0, so we're going to have 2 times 4 to the 0. Well, that, of course, is equal to 2 times 1, because anything to the 0 power is just 1. And so that's simply equal to 2. And so, we'll just keep going here. We'll put in a 1 now. 2 times 4 to the 1, of course, is the same thing as 2 times 4, which is equal to 8. And I think you can start to see why we pick these values, because if you go too much further, the graph is going to be way up here, and your graph just doesn't fit for these numbers here. So anyhow, this one's already up to 8. And if we do the next number, what are we going to be at? Let's see. 2 times 4 squared. Well, that's 2 times 16, which is equal to 32. And so that's not even going to be on the graph. So anyhow, let's go ahead and plot these points now. So what we're going to do is plot the points, and then after I get them plotted, I will then apply the 2 shifts, and we'll see how it goes. Okay, so looks like our first point is at -2, and at -2 would be right here, and it's barely 0.125. So as we saw in the first graph, this is kind of asymptotic. There's an asymptote right here. So I'll leave that as a dashed line. And then 0.5. For -1, we're at 0.5, so we just moved up a little bit. And at 0, we're clear up to 2. And then at 1, we're clear up to 8. 1, 2, 3, 4, 5, 6, 7. We'll put 8 right here. And see, so this thing sort of takes off and it almost shoots up straight up. And exponential functions do that. They take off and grow up real fast. And then, okay, so we have a point here, a point here, a point here, and a point way down here. And this just gets closer and closer to 0. Okay, not the prettiest graph, but anyhow, let's apply the shift now. So I'm going to use black now. Our shift, what we do is we take each of these points and we're going to go left 2 and then we're going to go up 1. So in addition, the asymptote that's here is going to go up 1. And now you can think of it as shifting also to the left, but this asymptote goes the entire x-axis, so shifting it doesn't do a whole lot, but going up 1 does. So it puts the asymptote right here now. So this is where our asymptote is. Okay. So I'm just going to put a dashed line going across here. There's our asymptote. It kind of goes right here, so I'm going to put that on like that. Okay, so now maybe I could use blue. If we shift this over 2 units, it goes over to there, and we go up here, that puts that point right there. So we go over 2, and then up 1. Same thing with this one. This one was at 1/2, right? So we go over 2 and up to the 1/2, puts it right there. This one was at 0, 2, so we're going to go over 2 and up 1, that puts it right here. And finally, we had this point here. We're going to go left 2, so it goes to here, and up 1, so it's going to put it right about there. That's it. So there you have it. We have our shifted function. And hopefully you can draw it a little bit more smooth than I did. But there you have it. So these are very similar to our square roots and our cube roots. You have horizontal shifts and vertical shifts. And now let's talk about the domain and the range. That seems to be a hard part for some students. So let's go over that. Now, if you're doing the domain, remember the domain is referring to the x's. So just look on the x-axis. As you go out, this axis here is the function here. Well, yeah, it is because this goes on forever this way, and there's an asymptote here. So, in fact, it goes on forever all through the x's. And it almost looks like it goes straight up here and never gets way over here, but it goes slowly and it keeps moving this way, and you might have to go miles and miles upwards before it gets way over here, but it does. It keeps going. So for the domain, it's pretty easy. And this will almost always be the same for almost all the exponential type functions. The domain will typically be x's equal to all real numbers. And that's almost always the case for exponential functions. Okay, so now the range though. The range is just a little bit different though. You'll notice in this case, there's nothing down here. You don't see any of the graph down here. There's nothing. Oh, and then right about here you start to see something. However, this point is an asymptote. So it's never really equal to 1, but it's always above 1. So the way we're going to state that, we're going to say y is bigger than 1. Notice we do not put that equal sign in there. It's never equal to 1 because that's an asymptote. It gets really close. So we want to take that off of there and make sure it's just that. So there you have it. We have domain and the range. Okay. That's a typical problem. Now, one thing you should realize about these graphs is that this is always what we call the initial value. Usually the variable that we're talking about is time in a lot of cases. And time is when it starts when time is equal to 0. So when this is 0, we get 2 here, just like we did right there. And that would represent the starting amount. We did finance problems where we started out and we want to know how long it's going to take for money to double or something like that. In fact, our next example I think has to do with finance. So let's look at that. Now here we go, exponential growth. This looks a lot like our interest formula one that we had, future value. But anyhow, the way our formula for finance was just a little bit different. It was like A is equal to the principal, and then it was 1 plus, remember it was R over M, and then we had it M times T. So very similar idea. Okay. But so this is our generic formula here. Now, this formula here will typically boil down to this. Okay, where the A is the same thing as here, and B is the growth rate. It's 1 plus R. And so sometimes we'll separate these two, put parentheses around that like that. Anyhow, 1 plus R is the growth factor. So let's just keep moving on. Okay, so here's an example. In 1970, the population of Kern County, California, where it's in Bakersfield, okay, was about 330,000 from 1970 to 2000. The county population grew at an average annual rate of about 2.4%. Write an exponential growth model given the population P of Kern County T years after 1970. About how many people lived in Kern County in 1990. Okay, so this problem, we will just, it's pretty easy. We just start out by writing that formula. We're going to say P is equal to the initial amount, and the initial amount is usually A, and then they have 1 plus R there, and then they have T here. Okay, so now we should take note here that 1970 is when t is equal to 0. Okay, that's what's meant by this information right here. It's the years after 1970. Okay, so this number right here is going to go in right here. The initial population is going to go in right here. And so this formula basically becomes, well, I don't know if I could write it here. See if I get enough room here. It's going to be 330,000. And I'm going to switch colors here so we can see it. And then 1 plus, I'm going to change this to a decimal. Okay, so percent means divide by 100, so that's going to be 0.024. So it's going to be plus 0.024 raised to the t, like that. And so now what we'll do is just simply rewrite this a little bit more conveniently as p is equal to 330,000 times 1.024 raised to the t, like that. Okay, so there's our generic formula for this one. About how many people lived in 1990? Well, what we need to realize is that this thing started when t was 0, and that was 1970. So if we go to 1990, that means t will be equal to 20. It's 20 years past that. And so that's what we put in here for time. Okay? Don't put 1990 in there. Okay? So again, this is a formula that says t years after 1970. So it's from that point. That's when t is equal to 0. So that's t equals 20. And so we just need to put we're going to put 20 in right here. And the rest is just doing it in your calculator, see what you get. And I'll leave that for you to do. Use your calculator and see what you get. You'll need to finish that part on your own. Alright, so let's go to the next slide. Compounded interest. There you have it right there. We've written it with n instead of m. Same idea though. And so we've had some experience with this equation. And so this shouldn't cause you too much confusion, but it will be a decent little review at this point. Again, the P is the initial principal or initial amount that you put. N is the number of compounds per year. And so let's try an example now. Whoa, let's back up there. So we're going to look at two different scenarios. And I'm going to set up the equation for you. I want you to go ahead and put it in the calculator after that on your own. So we have A is equal to P. And then we have 1 plus R over N. And then N times T. Okay? Well, the R, this is the interest rate right here. We're saying here that N is, we're compounding quarterly on this one. So for this problem, N is equal to 4. And just so you know, the one on this one, since you're compounding daily, N is going to be equal to 365. I think that's what we'll do for that one. Now the principal is the 4,000. It's always a good idea to change this to a decimal. So percent means divide by 100, so that's going to be 0.0292. And please, whenever you're dealing with exponential functions, you don't want to do any rounding in the steps here in the beginning. So don't do any rounding until you do your final step. And since we're dealing with money, your final answer you want to round to the nearest cent. But don't do any rounding in the beginning. Okay, so it looks like in case number 1, we're going to have, or part A here, we're going to have 4,000 sitting right here. And then we're going to have 1 plus 0.0292. And we're going to divide by 4 here. And we're going to multiply by 4 here. But let's see, how many years is this? That's 1 year. So we're just going to multiply by 1 there. Now, I recommend always doing this part in your head. it's real easy to make a calculation error. And so I'll let you do that calculation on your own. I don't care to waste your time doing that. And besides, you need some good calculator practice, so you'll do that. Try that on your own. If you need help on that, come back to me tomorrow, and we'll go over it together in class. Make sure you have the right answer there. The only difference for part B is that this is going to be 4,000, and then you're going to have 1 plus 0.0292 divided by 365. And then you're going to have 365 times 1. Okay, so try those two, and I think that finishes up our study guide or PowerPoint stuff. And so there you go. We'll stop right there. And then tomorrow in class we'll work on the book assignment and get that all done. Talk to you later.